Okay, hello again, sorry, welcome back. So in practice we don't have ideal switches, right? So we either have MOSFETs or IGBTs. So I as I mentioned, like one practical consideration that we should have for both inverters and rectifiers is that like we can't turn this one on and this one off instantaneously, right? So that's gonna cause a problem. So one thing that we do, we just gonna have some dead time. We're gonna have some delay between turning this one off and turning this one on. So we're gonna talk about that delay as we go through the table and through the voltage waveforms. But before that, let me also talk about a MOSFET package that we have. A MOSFET is a switch that you've seen before in your electronic courses and in this course before in 3130. It comes with an anti-parallel diode, right? So that can basically block the current going this way. It blocks the current going this way, but if you positive bias this one, basically it let the current go through this way. So it's called anti-parallel diode, or some people call it body diode. So either anti-parallel or body diode. And this actually comes very handy when we have a full wave inverter. So let's talk about the states that we have. So the ones that I have drawn in black are like what we had before. So if you remember, we had 1 1 0 0, and then we switched 2 off and switched 3 on, and then 1 0 1 0. So then these two stay on, but then we switch 1 off and 4 goes on, and then again we switch 3 and 2, so 3 goes off and 2 goes on. Okay, but now what we have to do to basically tackle that problem that we had for having two switches on the same leg on at the same time, we don't want that to happen. So what we do, we create some dead states. So the ones that I drew in red are basically the red states that we have added, right? So let's look at the first one. So in this first state, we had 1 on, 2 on, 3 off, and 4 off. Okay, so what is the next state? The previous next state looked like it was like everything like 1 and 4 stayed the same as before, but we wanted to turn 2 off and then 3 on. Okay, now we're gonna do that we're gonna create a middle state here, that we have 2 off and 3 off at the same time, and then we turn 3 on, right? So this is like basically a dead body, a dead state, a dead time that we are creating here. Before we turn 3 on, we have 2 off to make sure that we don't have 2 and 3 on at the same time, and then we turn 3 on. Okay, so let's look at what happens in that case. This is very important, so I hope everybody is following. So we had 1 and 2 on at the same time. So when 1 and 2 are on, then we basically have a current going through this one, going through here, and goes through here, right? The voltage across this is always going to be VDC in this state. The current, it might be going the other way based on the load that you have. Okay, now what we did, we kept this switch on. So this switch is on, right? But everything else is off. These 3 switches are off. Sorry, these switches are off. So let's assume that the current that goes through the load is this way, as we assumed previously, right? So the current that goes through the load is this way. So this switch is on, right? This current needs a path to go through, right? So this switch is off, this switch is off, this switch is off. So it would find its path through this diode, this body diode of MOSFET number 3, okay? So what happens here is that we have current going through this diode and goes back through the switch here, okay? So this is basically what's happening here. And we're not going to ignore the bias, the forward bias voltage of the diode. So let's just like just take those into consideration. So if that's the case, if the current is going through this way, if the load current is going through this way, so for example, if this is a resistive load, if the current is going through this way, then the voltage across the load, it's gonna be negative VFD. Why is that? Because we have VFD voltage drop against this, across this diode. So this one is gonna be negative VFD based on the polarity that we chose for our output voltage. Okay, let me actually write this a little bit smaller. Okay, but as I mentioned before, we don't know exactly the direction of the current. If we have a motor or inductive load, the current might be actually going this way, right? So what if the current is going this way? If the current is going this way, this switch is on, right? This switch is on. The current is going through this way, right? So this current has to find a path to go through. So it finds its path this time through this diode, right? So it would basically goes through here, then goes through here, then goes back to VDC through here. So it basically now it has this path. As I mentioned, the direction of the load current, we don't know what it is. Like, it depends on the load that we have. If you have a resistive load, it's very easy to make that decision. But like if it's an inductive load, then we don't know the direction of the current. So like that's why like I'm doing it for both of the cases. So if the direction of the current is this way, now this diode is gonna let the current go through it, and then it goes back through switch 1. So now what's gonna be the voltage against the load? This point, it's connected to VDC, so this node is gonna be VDC, and here we have 0 minus VFD, right? So the voltage across the load, it's gonna be VDC plus VFD. So it's gonna be either this case or VDC plus VFD. Okay. In many textbooks, like they only do it like either